Hello everyone, I'm Huang from Tsinghua University. Today I'm presenting TapeOBS, a cost-efficient archive cloud storage service in Huawei Cloud. We introduce tape into a cloud object storage archive tier and make it work for production scale. Archive storage is for data that is rarely accessed but must be retained for long periods, such as medical records, backup files, video materials, and logs. The system objective is not low latency or throughput. It is cost efficiency over performance. Now, why do archive storage in the cloud? Cloud-based archive storage inherits several advantages from cloud: automated lifecycle management, virtually unlimited scalability, and global accessibility. Users can set policies to move data from hot to cold tiers, and the service handles placement and retention. Today, essentially all major cloud providers offer archive storage services as part of their storage portfolio. Historically, our archive service was HDD-based, but HDD archive is still relatively expensive for massive cold datasets. We introduced tape because tape has strong cost and sustainability advantages over HDD. More than 50% lower price, more than 2 times longer lifetime, and the total cost of ownership is 4.95 times lower. It also has a much lower carbon footprint, 97% less CO2e emissions. Tape may sound like an old technology, but it has kept innovating. It has a clear technology roadmap with capacity projected to grow 32% annually from 2024 to 2034. These properties make tape extremely attractive as the physical substrate for long-term data retention. But tape is not a cheaper disk. Its basic building block is the tape library. It is a very different hardware system. A tape library contains many cartridges that hold data, multiple drives that can read or write tapes, and a robotic accessor that physically moves cartridges between slots and drives. 3 hardware features matter most. First, the library has high density, about 10 petabytes per library in our platform. Second, it has a low drive-to-tape ratio. In our configuration, 4 drives for 1,000 tapes. Finally, switching a drive from one tape to another is slow, about 80 seconds, including rewinding and unloading, robot movement, loading, and seeking. With that hardware reality, we built TapeOBS, a tape-based archive storage service. TapeOBS is a single AZ object storage service that uses append-only units called plogs to store data. The system has 4 major components, as shown in the right figure. The service layer exposes OBS APIs and handles user requests. The index layer maintains the mapping from object IDs to plogs. The persistence layer stores plog data in tapes, and DataBrain schedules non-real-time tasks like garbage collection. Here is the workflow. For a write example, suppose the user writes a 4 MB object and we use EC4 plus 2. First, the service layer creates a plog and appends data. Then, the plog client divides the object evenly into 4 1 MB data chunks and generates 2 parity chunks. Next, the persistent layer stores these chunks in tapes. Finally, the service layer inserts the object ID to plogs mapping into the index layer. For reads, the workflow is similar. The service layer queries the index layer, then issues a plog read to the persistence layer. So, what principles guided the design of TapeOBS? We align with tape hardware at 3 scales. At the tape pool scale, we make reads and writes asynchronous, so that we can hide the limitation of tape hardware. At the tape library scale, we minimize drive thrashing. Namely, we try to avoid frequent tape switches on drives as much as possible. At the tape scale, we avoid random reads within a tape. These 3 principles are necessary conditions to make tape viable under cloud workloads. Next, I'll walk through the concrete mechanisms for these principles. First, we make the tape pool fully asynchronous. TapeOBS maintains a small HDD pool whose capacity is about 4% of tape capacity. This HDD pool acts as a temporary staging area. Therefore, all reads and writes to tapes can become asynchronous. The payoff is that we can schedule a large amount of data to and from tapes in a bulk manner. Bulk scheduling is a superpower that tape needs. We can reorder work to reduce tape switching and preserve sequential streaming. Let's look at the restores. Our observation is that archive services typically have hour-level SLA for restore. Users usually restore an object first and then read it later. A standard restore SLA in Huawei Cloud is 5 to 12 hours. So our approach is, we asynchronously copy objects from the tape pool to the HDD pool to serve restore requests, and crucially, we reorder restore requests so neighboring requests tend to target the same tapes. This reduces three costs: drive thrashing, frequent tape switching, and seek time. We apply a similar idea for writes. The observation is that users can set expiration time for buckets and objects, which lets us estimate lifetime. So, in TapeOBS, writes are first absorbed by the HDD pool and later flushed to tape asynchronously. During flushing, we try to move objects with similar lifetime onto the same tape. The benefit shows up later. Garbage collection overhead in the tape pool is reduced because objects on the same tape are likely to be deleted around the same time, leading to fewer partially dead types and fewer expensive tape-level GC passes. Next, to minimize drive thrashing at the library scale, we introduce dedicated drives. We statically divide drives into three groups. Write drives serve object writes. They keep appending data on a tape until the tape fills up, which is naturally sequential. Read drives serve object reads and restore requests. These requests come from users and are non-deterministic. Internal drives serve consistency checking, easy repair, and garbage collection. These tasks typically focus on the same tape for a long time. By separating these workloads, we prevent internal long-running jobs from being constantly interrupted by random restore bursts. The net effect is fewer tape switches and more stable throughput. As described before, the service layer turns object writes into a plog append, then applies m plus n erasure coding, and it produces m data chunks and n parity chunks and distributes them across different tape racks, treating each rack as an independent failure domain. It has a direct implication on restores. For read requests, fetching an object involves many drives, leading to drive thrashing. To address it, we proposed batch erasure coding. Instead of doing EC per object independently, the service layer aggregates multiple objects into a single plog append call and codes them into a batched way. This lowers the probability that any single object spans many tapes, which in turn reduces the fan-out of restored reads. So far, I've described system-level scheduling and placement. Now, let's zoom into the local storage engine that actually talks to the tape library. Each tape library is connected to a head server, where a local storage engine runs. Its job is to efficiently write and read plogs, bridging the high-level scheduling decisions with low-level tape commands. Our head server configuration is 2 12-core CPUs, 189 GB DRAM, 2 3 TB NVMe SSDs, and 2 NICs connected to 2 top-of-rack switches. The key point is that this local engine uses SSDs for buffering. The first component in the storage engine is a virtual database, or VDB, implemented as 2 SSD key value stores, metastore and datastore. Metastore stores metadata of all plogs in this tape library. The key is plog ID, and the value includes plog ID, tape offset, size, plog state, and other metadata. The purpose is to avoid random metadata accesses on tapes. Datastore temporarily buffers the data of plogs. The key is plog ID offset, and the value is a fixed-size data slice. Data from a plog is flushed to tape in batches, maintaining sequential writes. The second component is a tape library scheduler, which streamlines access using read scheduling and flow control. Let's start with read scheduling. A modern tape is composed of hundreds of wraps that are logically connected, as shown in the left figure. Random reads can induce expensive back-and-forth movements, so we use a scan algorithm to generate an access ordering to plogs, reducing seek time. Even with good ordering, tape performance can degrade if the host submits I/O in a jittery way. The issue is, jittery I/O submissions can cause the drive to incorrectly estimate host speed and then the driver may select a low speed, leading to performance degradation. Our approach is flow control. We align the speed of submitting requests with the speed of the tape drive. As shown in left figure, with flow control, performance becomes more stable and there is no degradation. TapeOBS started gradual rollout, grayscale release at the end of 2022, and officially began serving customers in 2024. It has stored hundreds of petabytes of raw user data. We run several clusters, and each cluster has multiple tape pools. Each tape pool is equipped with 14 tape racks, giving a total capacity of 140 petabytes using erasure coding 12+2. The remaining slides provide workload observations. This figure plots the distribution of object size in our production workload, where the x-axis represents object size and the y-axis shows the cumulative proportion of the total TapeOBS storage capacity occupied by objects smaller than or equal to this size. We can observe that the object size exhibits a highly skewed pattern. Objects smaller than 500 megabytes occupy 93% of TapeOBS storage space. This figure shows a 24-hour interaction between the HDD pool and the tape pool. It tracks HDD pool utilization over time and also reflects tape side ingestion. We can observe that the utilization of the HDD pool fluctuates between 71% and 71.675%. TapeOBS digests data at a relatively constant rate from the HDD pool to the tape pool. This figure plots the throughput of tape pool operations over a 24-hour window. It separately shows write throughput and read throughput. We can observe that, first, the tape pool delivers a write throughput with an average value of 100 KOPS per minute. The read throughput is low. Second, HDD pool triggers GC periodically, resulting in periodic spikes in read throughput. This table summarizes failure behaviors observed in tape libraries. When these failures occur, EC can provide availability for read operations, and the HDD pool can provide availability for write operations. Let me conclude. TapeOBS is a cost-efficient tape-based archive storage service in Huawei Cloud. It is built around three principles. First, at tape pool level, we make reads and writes asynchronous using a small HDD staging pool. Second, at tape library level, we minimize drive thrashing through bulk scheduling, dedicated drives, and batch erasure coding. Third, at tape level, we avoid random reads through a tape-tailored local storage engine with scan-based scheduling and flow control. TapeOBS began its gradual rollout at the end of 2022 and officially started serving customers in 2024. TapeOBS has stored hundreds of petabytes of raw user data. Thank you for listening. If you have any questions, I recommend you to contact with Wang. His contact information is below. Thank you.